may wonder, is there anything like green chemistry? Chemistry is colorless. Of course, it has all colors embedded in it. It has all colors, red, green, everything. But what is the speciality about the green chemistry? So it is a green chemistry is a recently introduced concept. This was introduced because of the devastating destructive effects of the chemical industries, chemical pollution going on in the world. How to control this? In order to control this, for all these chemical industries, automation, textile industries, or thermal electricity generation units, in all these activities, the chemistry is behind this. Various chemical reactions are going on in this process. Because of these industries and chemical industries, chemical process, toxicity in the environment is increasing. Unless we control this toxicity, even our habitation on this earth becomes a problem. So to mitigate this toxic, hazardous effects of chemical industries on earth, they have introduced a concept, what is known as green chemistry. This was introduced in the year 1990 by the Environment Protection Agency of USA. So what we try to focus in green chemistry is that we have to develop the chemical methodologies, reactions which are environmentally non-hazardous, environmentally non-harmful, so that the environmental system remains as clean as possible and less harmful to the various living organisms. So in this connection, I would like to I'm just given half an hour time, so I may not be able to cover all the aspects, but anyway, I would like to give a brief overview of what is green chemistry. So of all the planets we have available, of course 9 planets are, we know, and one more planet is reported to have been discovered, and it is yet to be confirmed. But anyway, Earth is one of them. The major components of Earth are the atmosphere, lithosphere, the biosphere, hydrosphere, biosphere, and anthrosphere. These are the important units of our environment. Atmosphere is the air blanket, lithosphere is the rocky mass, biosphere is various organisms living on Earth, hydrosphere is water cycle, and cryosphere is ice, is related to ice, how it is formed, the dynamics of ice, chemistry and all that, and anthrosphere is about the human beings. So these are the main ingredients of Earth. We have to look at the point of environmental hazard. Next slide. So come to hydrosphere. Hydrosphere is a water cycle. Sea evaporates water and it goes in the form of clouds. Sun is there, snow melting, mountains. Again the water comes here, it evaporates, it goes back as clouds to water, rain, lakes and all that. This is how the hydrosphere exists. Water equilibrium in nature, vapor, liquid, solid. It is a dynamic process, it goes on. So this dynamic process, if it has to go, we have to keep the environment as clean as possible, as less toxic as possible. Otherwise, this hydro cycle or this water cycle will be disturbed. Water cycle is disturbed, rain falls, tsunamis, then storms, all these hazardous events will occur. Again, the life becomes difficult on Earth. So in order to maintain a good life, good quality of life on Earth, you have to maintain this hydrosphere water cycle. How you can maintain? You can maintain this only when we maintain the pure environment. If you want to maintain the pure environment, you need to do green chemistry. Next. Next. Yeah. So in the case of biosphere, you have got the microorganisms, virus, bacteria, and all that. Plant life, various types of plant life, animal life, human life, and all. So this is the biosphere. Next. Next. Yeah. Here you have in the nature, in the early days, we used to have the clean mountains, ice caps, then water, very clean, flowing rivers. Everything was everything was clean and beautiful in early days. But after this industrialization, this water gets polluted, the ice melts, and then everything will be hydrocycle and all that will be disturbed. Next. Yeah, you have got animals, very amazing, life on earth, animal life. You have got animals, plants, various types of organisms living on earth. This is all because when the earth is green, everything will be okay. Next. You have got amazing oceans. So oceans are wonderful gifts given by God to us. You have to maintain them as few as possible. Again, this is possible by maintaining the ecological equations in the nature. Next. Yeah, if you look at the effects on all the components of Earth, pollutes air blanket in the atmosphere, destroys rocky mass in lithosphere, affects life of living organisms in biosphere, disturbs water cycle in hydrosphere, ice melting occurs in cryosphere, human world is destroyed in anthroposphere. All these, all these drawbacks, effects will be there because of the chemical pollution. So there is a great need to prevent chemical pollution of air by green chemistry. Next. Yeah, some examples I will just like to quote about the effects of the chemical industries on the environment. Next. Yeah, you might have heard the Bhopal gas trial. This occurred in the year 1984. It is due to the leakage of methyl isocyanate. Occurred due to the leak of methyl isocyanate. MIC is used to manufacture the cork-mode pesticides, which are used very widely at that time. About 30,000 people died in this gas leakage. Lakhs of people are affected. This MIC, the cork-mode pesticide manufacturing is used. This gas leakage occurred. It's highly toxic gas. If you inhale the gas, you become blind, your nervous system gets affected. This is how the people died. Nearly 30,000 people died. Officially, unofficially, we don't know how many died. Okay, next. Yeah, another famous example is pesticide DDT. This is a dichlorothimethyl. This compound was a pesticide. This compound was also responsible for the damage of the environment because it's highly toxic. It causes cancer. Used to control malaria and typhus. It's a pesticide. It's non-biodegradable in the environment. Its residues will cause cancer. And hence this molecule as pesticide was abandoned. Nowadays it is not used. Next. Yeah. Another important effect of the chemistry which we are doing is acid rain. Occurs due to SO3 NOx gas in the atmosphere. So H2O, H2O will be formed, nitric acid will be formed. This when we form with the rain, you get when this gas is dissolved in rainwater, you get acid rain. When acid rain falls, you see the trees are defoliated. All the leaves are dropped, only stems remain. So it has a devastating effect on agriculture, food production, water quality, buildings, metal structures, statues, etc. So if you have acid rain, everything will be corroded, everything will be destroyed. The pH of the agricultural land also alters, the production of the food drops, everything will drop down. So this acid rain is one of the consequences of indiscriminate practice of chemical industries. Yes, next. Yeah. Another effect is the global warming. So this global warming is increase in the temperature of Earth's near surface, air and oceans occurs due to greenhouse gases. These greenhouse gases again are the products which are formed in the chemical industries, like water vapor, carbon dioxide, methane, N2O, O3. All these gases, automobile industry, thermal industries, in all these industries, these gases are produced and they are responsible for the global warming. So this global warming causes adverse effects on weather, ecology, and destroys the congenial global atmosphere ambience for life. Greenhouse gases, mainly H2O and carbon dioxide, they trap solar radiation, hotter wavelength, and retain its heat radiation, that is radiation of longer wavelength. And if it retains the heat, the warming of the weather takes place, and that causes all the important destructive activities. Next. Another one is the ozone hole. This is the ozone hole O3. This is there in the atmosphere. Depletion of O3 layer in Earth's atmosphere. So stratosphere it is there, 20 to 30 kilometers above the surface level. You have got this ozone layer. When there is ozone depletion, you get the ozone hole. Because of this, what happens? You get O3 layer absorbs 99% of sun's UV light, that is 200 to 350 nm of lambda, which damages exposed light of organic matter. So if ozone blanket is not there, UV radiation comes to Earth, it destroys the living organisms. A lot of research was done on ozone by GMB Dobson of England, and he has estimated the concentration of ozone by Dobson spectrometer, and the units in which ozone concentration is expressed is what is known as the Dobson unit. So ozone hole or ozone layer also is a very important thing which should be there in the atmosphere. If ozone layer is damaged, destroyed, all the UV radiation from the solar system will come down to Earth, and UV radiation has a very destructive effect on the living organisms. And hence, you have to protect the ozone layer. If you want to protect the ozone layer, we should not leave harmful gases into the atmosphere. Again, where from you get the harmful gases? By chemical industries. Chemical industry means you are doing the chemistry in a most hazardous way. You should do the green chemistry so that toxic gases are not released, ozone hole will not be there, ozone layer will be protected as a unit in the atmosphere so that solar UV radiation will not travel through the Earth, damage the living system. Next. That is why, because of all these drastic effects of chemical industries, we need to worry about what we should do with regard to the current practices of chemistry, how we can mitigate them, how we can eliminate them. That is where the role of green chemistry comes in. Next. What is green chemistry? Green chemistry is nothing but eliminate pollution through the invention of new industrial processes that do not use or produce environmentally harmful substances. So main objective of green chemistry is this: we should not produce harmful substances. Then, in short, it is an approach that prevents formation of waste at source. Even while carrying out the reaction, the wastage, unnecessary chemical products are to be eliminated. We should not produce a waste, chemical waste. When you produce chemical waste, that damages the environment. Of course, so this is denied by design. That is green chemistry. Next. What are the objectives of green chemistry? It reduces production of waste, avoids excess use of materials, minimizes hazard, prevents risk, economizes energy, overall minimizes the cost. So these are the objectives. Everything is good. So if you can achieve the avoiding waste, economize materials, avoid hazards and risk, energy, and cost, all these parameters are will be organized or will be managed by means of the green chemistry. Hence, there is a great relevance, there is a great demand for practicing green chemistry. Next. Yeah. So there are, of course, we have given about the principles of green chemistry, 12 principles. One is the prevention of waste, chemical process. We should avoid waste. Preventing waste is better than treating or cleaning up waste after its creation. These are fundamental principles. For doing any chemical industry, any chemistry, you should not produce waste. You should produce only the compound which you want, which you are going to use 100% without any of other products, byproducts, unused products. When you leave unused products in the environment, they cause damage to the system. Next. Of course, these are various principles. There should be less hazardous chemical synthesis, designing of non-toxic chemicals, non-toxic solvents, auxiliaries are to be used, reduce derivatives of products, use of renewable feedstocks. That means the reactants which you use, they should be renewable, they should be non-exhaustible. Always they should be available. And then catalysis, the catalyst and reagents used must also be eco-friendly and efficient. All these principles you have to concentrate while planning a reaction by means of green chemistry. Next. The most important principle in green chemistry is atom economy. That is, when you carry out a reaction, see, synthetic methods should be designed to maximize the incorporation of all materials used in the process to the final product. Carry out a reaction between the X plus Y. X plus Y should be in the case of products. There should not be any unwanted product. Usually when we run a reaction, we have got X plus Y as a reactant, get a product, along with it you get unwanted product also. This unwanted product is toxic. So as far as possible, you should avoid the formation of unwanted product. All the reactants should be made to transfer the products which are of direct use, so that there is no waste, economy of the substrates, economy of the energy, everything will be green, and hence that is the atom, all the reactants will be converted to product. So atom economy will be more, that is economically viable reaction. And also you are not producing any unwanted substance. It is less hazardous from the point of view of environment, and hence the reaction will be green. So how you calculate the yield? Of course, these are the equations on which you can calculate the percent yield of a product, selectivity of an isomer or atom economy. How you calculate? These are the equations. Next. Examples, I will give one or two examples. For example, if you want to prepare the malic anhydride, one option is benzene oxidation. If benzene or oxidase, you get malic anhydride, you get the side products also, carbon dioxide and water. Look at the atom economy here, it is only 44.7%. So it is not advisable from the point of view of green chemistry. On the other hand, if you make this malic anhydride by means of, in the case of butene oxidation, just to take butene, presence of oxygen, either butene or oxygen is non-hazardous, total thing will be converted to malic anhydride. Only water is eliminated, water is not toxic, less toxic. Apart from all these things, the atom economy is 64%. So this is the best option for making malic anhydride. This is the green chemistry we should look for, not the other methods. Next. You have got, if you look at the various chemical reactions, some atom economic and atom uneconomic reactions, you have got atom economic reactions like rearrangement, addition, disorders, other concentrated reactions. In all these reactions, there is no elimination of any material. Just A plus B adds on, or the molecule gets rearranged. The bonds will be reorganized, and hence there is no loss of any material, and the energy required will be less. You are not using any toxic reagents to affect the chemical reaction, and as such, these reactions are advisable to make a product by means of green chemistry. But these are atom uneconomic, because of substitution. When you carry out a reaction by means of substitution, always there will be elimination of a product. Similarly, eliminations will be there small molecules like water, alcohol and something like they get eliminated and introduce an unsaturated molecule. Basic reaction always trialkyl phosphine is the byproduct. It is hazardous, and thickener to magnesium halide is the byproduct, again toxic. So uneconomic reactions are not the best option. If you want to produce a molecule, you should look for atom economic reactions, so that there is no waste, total substrates are converted into the desired product. Next. Yeah, when you want to make a green synthesis, you should take into account the 12 principles of green chemistry: reaction with high atom economy, high yields, environmentally benign. All these 4 points you should look into in order to make a green chemical synthesis. Yeah, I will do some examples on green chemical synthesis. Yeah, rearrangement reactions. The atoms that comprise a molecule will only reorganize itself orientationally to one another. It can be affected by thermal, photochemical induction in presence of a catalyst. Classic examples, you have a number of examples of rearrangement reactions. You have benzoic acid rearrangement, where a ketone, a diketone is converted to alpha hydroxy acid. You see, this reaction you can again convert this diketone into alpha hydroxy acid, either in the conventional procedure where you get a very toxic reagent like 50% potassium hydroxide solution ethanol, you get no doubt alpha hydroxy acid, but the reagents are highly corrosive and they are not green from the environment. Alternatively, same reaction you can run with a trace of sodium hydroxide, potassium hydroxide, without using any solvent. 100 degrees, just 20 minutes reaction, you get alpha hydroxy acid. Very nice. So the green context is, this is solvent-free procedure in atom shape. Almost 90% of the reactant is converted into the product. Next. Yeah, this is the mechanism. I don't go into the details. Next. Oxyamide. Beckmann rearrangement. Take an oxide, presence of acid, chloride gets protonated. Then you get the carbonium ion. Water adds on. You get the amide. Oxide converts to amide. This is a Beckmann rearrangement. It is environmentally green because there is nothing is lost. This reaction is used in the manufacture of nylon 6. It is used in the manufacture of pipes, nylon fabrics, etc. And this one is caprolactam molecule, hydrolysis at nylon 6. How do you make caprolactam? Caprolactam again, cyclohexanone oxide. Take volume, H2SO4 concentrated, get caprolactam. This is environmentally hazardous procedure. Whereas you take a zeolite, it's a green product. Zeolite is nothing but a solid acid, and it is not toxic. At the same time, it is effective. So zeolite green process, zeolite method of conversion of cyclohexanone oxide to caprolactam. Here is 75%. Atom efficiency is also more. So caprolactam, once you get, just hydrolyze it, you get the polyamide, which is nylon 6. Nylon 6 is industrially it is manufactured. How do you manufacture this? You can manufacture, take cyclohexanone, use a lot of volume sulfuric acid, convert, but using sulfuric acid and all that is highly hazardous, highly toxic. So hence you should not go for this. You should go for green process. Use a zeolite material which acts as a Lewis acid, and then you get the caprolactam, hydrolyzed nylon 6. So the entire thing is green. So no non-hazardous. Next. So rearrangement reactions. So the starting material and the end product both contain the same atoms, and therefore no waste generation, and display a total atom economy. So rearrangement reactions are always the things which you have to look for in the case of green chemistry. Drastic hazardous external conditions are not required, hence eco-friendly. Want to make a product, as far as possible, should choose a reaction which you can do with just rearrangement of the particular substrate. Yes. Then addition reactions. These are also good reactions from the point of view of green chemistry. Addition of reagent to unsaturated groups. You get this. Here, electrophilic addition. Of course, I will not go into groups and all that. Carbocation, stability. Next. Yeah, here halogen addition. For example, if you have a double bond, you can add to this a dibromide. You can prepare. You can do it either conventional way and green way. Conventional way is just take a bromine, dichloromethane, you get the dibromide. This is not hazardous because you are using bromine itself and you are using dichloromethane. The dichloromethane also highly carcinogenic. It induces cancer. Hence, this methodology is not good. Go for alternative methods where hydrogen bromide is used, HBr is used in place of hydrogen peroxide. You get this same dibromide. Medium is ethanol, again it is green, non-toxic. And hence this procedure is the one we should opt in order to make this dibromide. Next. Yeah, these are mechanisms. I don't want to go next. Yeah, take Diels order reaction between furan and malic acid. Diels order is just addition of a diene and dienophile. You get the adduct is there. So this Diels order production is a very important reaction. The manufacture of many industrial usable compounds. The green context is the reaction carried out in aqueous medium here, avoiding benzene, exchange at room temperature itself, 100% atom exchange. Here, this Diels order is run in benzene, the conventional procedure, not good. But same reaction you can do in water, room temperature, you get this adduct. So this is the green procedure. Should look for this. Look for next. Yeah, this is the mechanism how we should go here. Yeah, what is the important application in mass Diels order is important is the manufacture of this aldrin. Manufacture of aldrin is an important pesticide. It's a complicated molecule, multi-halogen substituted system. Very difficult to prepare otherwise. So you have to go for a Diels order procedure where you can do it just traces of sodium hydroxide. You can do it and get this product which is industrial. So atom efficiency is also very good. So atom economy is nearly 82%. You see the whole reaction is under traces. Green chemistry of additional next. So what is the green chemistry? All the reagents are consumed. Addition reactions are green because all the reagents are consumed. Equimolar quantities of reactants are converted into the product. No additional byproducts are formed. If allowed by the reactants, reuse is a good synthetic cell. So if you want to make a product, always go for addition reactions. Next, concentrated reactions. These are pericyclic reactions. So what again this Diels order is one example. Next. Yeah, you know what you can classify these concentrated reactions as cycloaddition, sigma-tropic reaction, and then electrocyclic reactions. This depends on how many sigma bonds are produced, no sigma bond is produced, one sigma bond is produced or broken. So the types of pericyclic reactions are distinguished by the number of bonds made or broken. Here you see 2 bonds are made here. So these are cycloaddition, sigma-tropic reactions, electrocyclic. Here one sigma bond is one bond is broken or one bond is made. All these reactions are green because there is no toxic reagents are involved in this chemical process. Next. Yeah, again, you may ask what is the use of this rearrangement. Here you see the synthetic importance of pericyclic reactions. Diels order reactions, here you see 1, 2, 4, 5 is used as a reagent, acetylene is used as a dye here. Enophile adds on, you get the pyridine, multi-substituted pyridine molecule. Pyridine is very unreactive, as you know. It's an aromatic system which does not reluctant to undergo any reaction, but still you can introduce all the desired substituents, all carbons, with this wonderful reaction named Gibbs order, lysine, basically you get this pyrimidine molecule, which is a very important raw material for various pharmaceutical industries. Yes, yes, yes. The green chemical aspects can be carried out heating light only, no hazardous way of heating, atom economy is high, commercially beneficial, eco-friendly, and hence all addition reactions or rearrangement, sigma total, all these rearrangement reactions are green. Yes. Uneconomic reactions, okay. I don't want to go into details, we don't have time. Next, substitution reactions. See, for example, in the case of industrial manufacture of phenol. So earlier, what we do is you take the genuine sulfuric acid, heat this with sodium hydroxide, 300 degrees, you get the phenol, elimination of sodium sulfide. This is non-green procedure because genuine sulfuric acid itself is hazardous, sodium hydroxide is toxic, temperatures are using is high energy. So here high economy cost of production is more, and atom economy is also less because sodium sulfide is a byproduct, hence the atom economy drops down. So from the terms of chemistry, from the terms of economy, this is not a designed way of producing phenol industrially. But you may ask how we can produce phenol industrially in green way. Alternative is to take the cumene, it's isopropyl benzene, just oxidize this. So the oxygen gets inserted here, you can see it bond, OH gets substituted to the aromatic system, you get the phenol and acetone. Here the wonderful aspect of this reaction is that both the products, both phenol and acetone are useful, and just oxygen reaction, no corrosive reagent, everything is wonderful. So this is green. Want to make a phenol, what is the option? Should not go for the earlier one, should go for the oxidation of cumene. So green, economic and all. Next. Green chemical substitution reactions. Okay. Elimination reactions again. These are not atom economic because always there is elimination of byproducts. There is a production of unsaturated molecule. Yes. Next. These are various details. Time, no time. So again here, for example, dehydrohalonation of alkenes. This is an important reaction in the petroleum refineries. Heat, you get the elimination of hydrogen and you get the unsaturated molecules. Dehydration of alcohols, 160 degrees, again base. So you have to run these reactions at a eco-friendly condition. Next. Yeah. This is Hoffman elimination. You might have, it's a textbook reaction. You might have studied this. Elimination. You take water ammonium salt and then heat it. The importance of this is you can increase the terminal olefin system attached to a cyclic molecule. So this is a very interesting, but this is a heat elimination of and all that. It's not advisable. Alternatively, you take this molecule, keep this with sodium silver oxide, add some sodium hydroxide, you get the expansion to the insertion of the dose. This is the internal unsaturation. Green chemistry in this reaction, there is no loss of acid, atom, economy, improves. Yeah. This elliptic reaction again is very important reaction to the manufacture of the olefins. Yeah, next step. You can run these reactions in a regular way, which are gastric. In chemistry of, in terms of green chemistry, in fact, the very ordinary. You just take this molecule, and oxide, oxygen, acetate, just water, room temperature, you get the sodium. So this is a green way of producing the olefins by means of this reaction. Next. Yeah, these are mechanisms and all that. Next. Yeah. So in most of the chemistry and chemical reactions, you can't practice chemistry without oxidation reduction process. These are important reactions in chemistry, either oxidation or reduction. For example, you take oxidation of methane, methanol, then you get the formaldehyde, and then you get this acid, and then carbon dioxide. Ultimately, so you take methane, you can oxidize to carbon dioxide. You can do the reverse also. For doing this, you use very drastic reaction conditions, like reagents, high temperatures, and all that. But you can avoid all this by using electrochemical methods, electrochemical oxidation reduction you can do, so that it is eco-friendly and green. Alternatively, you can think of using the biocatalysts like yeast, enzymes, and things like that, which are environment friendly, so the system becomes green. You can run all the reactions by means of this eco-friendly reagents like electrochemical oxidation reduction or biochemical catalysts like yeast, enzymes, and proteins. So another important aspect to run a reaction is you have to run the reaction in a solvent medium which is non-toxic. That is very important. So water is of course advisable. Water is the most advisable way of doing these reactions. Some examples are given: epoxidations and all that, opening of epoxide ring, you get this cis diol and all that. Here leaves are again in water, you get an acid reduced to RNA. All these are green reactions. You need not run the reaction in benzene or hazardous solvents. In water, you can just run the reaction. Yes. These are some examples which I don't want to go into details. Next slide. A mechanism. Next slide. Next. Yeah. Okay. So reaction in ionic liquids. Ionic liquids are wonderful reaction medium. You can run the reactions in the ionic liquid, so that you can run the reaction very effectively and in a clean manner. Next. These are various ionic liquids. Next. Of course, carbon dioxide. Carbon dioxide gas. You liquefy this, you get liquid carbon dioxide. Liquid carbon dioxide is a wonderful reaction medium. Next. For the development of this synthetic methodology, for the synthesis of various proteins and peptides. Here you see protection, release and protection, expansion of various peptide links will happen. All these solid phase peptide synthesis that can do. For this work, it was awarded Nobel Prize. Next. Then green catalyst oxide, phase transfer catalysis in green. Next. These are all mechanisms how the phase transfer works. Yes. Next. And these are various types of phase transfer catalyst reaction examples. These examples, various PPCs. Then you have biocatalysts again, which are green. Yes, biocatalysts. Yeah. Chemoselectivity, detoselectivity, enzymatic systems, enantioselectivity, various examples. Asymmetric biocatalysis, again, various examples. These are all green chemistry, yes. Blue biocatalysis, yes. Biocatalysis. Yeah, just one earlier slide. You see, hydration of for 40 days is a biocatalyst. You can convert to citric acid directly. It's a wonderful green reaction. Yes. Next. Open up this oxidation reaction. Next. Yeah, just so here industrial production of the penicillins. You know, penicillins are important antibiotics. So you can take the sugar syrup in the bioreactor. You can add isogenium. Isogenium is the catalyst, biocatalyst. Entire sugar syrup is converted to penicillin. Penicillin is a very complicated molecule. Beta-lactam, and then substitutions, then cell-dimethyl groups, and the compounds here. Very difficult to prepare conventionally. But you see, very nicely, you take a corn syrup and then use the isogenium biocatalyst to convert it to total the mass is potential gene wonderfully. It's a green, it's a absolutely green method. This can be acylase, 6-aminobenzoic acid, expanded, you get this full system. Again, you condense this with phenyl glycine, with ampicillin, amoxicillin, and then this molecule you condense with the fluoxetol and cyclohydroxy. All these complicated antibiotic molecules we can just prepare by means of biocatalysis. Make these molecules otherwise very difficult. Yeah. Yeah, green biocatalysis, yeah. Microwave technology. No, I don't have time to work these things. Yes. Yes, these are various examples. Ultrasound. Then you have what next? These are all various examples. Photochemistry. Photochemistry again is a very wonderful way of energizing the reactions to convert them into products. Yeah, next. These are various examples. Just one thing here. Yeah, in case of field-Crafts reaction, you want to run a field-Crafts reaction, you have to use a Lewis acid like aluminum chloride or very strong and toxic. So here you see photochemically, you take control an aldehyde, acylation, very nicely you do. You get this acyl is the important intermediate for manufacturing various drugs like dipom, hypophilia, diazepam. All these are drugs which are made from this acyl proteins, which are made by photochemistry of control. So photo energizing of reaction is also green. Yeah. So what we can say finally is natural photochemical phenomena, green process, have contributed to the creation, evolution, sustenance of life on Earth. That too, like green chemistry, dynamic equilibrium, all chemical elements in presence of sunlight. Because of this photochemistry, they are converted into the carbon dioxide, H2O, NH. These are the basic molecules for life and other organisms on Earth. Again, these molecules they are converted into carbohydrates, hydrocarbons, alkaloids, in case of plant life. The other route is proteins, microbes, and animal lives. Again, the reverse equilibrium occurs. They decompose, get carbon, water, and carbon dioxide, go back to elements again. It's eternal cycle. It goes on Earth due to this photosynthesis. Yes. Yeah. No, earlier. So the driving force for the phenomena of eternal interconversion of chemical elements into energy, matter, living non-living, which is green chemistry. So this dynamic phenomena of eternal interconversion of elements into life into elements is green chemistry. Those by green chemistry. So green chemistry sustains matter, life, life cycle process in nature. One has to observe keenly the chemistry of nature, learn them, and judiciously try to repeat them in our labs, industries, so that we can sustain life through green chemistry. Yeah. So earth, nature, green chemistry, this is the let us do chemistry as nature is doing, because nature is the best chemistry. Do things non-hazardous way, non-harmful, no damage to the organism, no damage to the life evolution system, no damage to environmental components. So what we are doing is half-knowledge chemistry. I would say this is red chemistry. So we have to do chemistry, practice chemistry, industries, chemical industries, as nature is doing. See, nature, for example, it makes carbohydrates, it makes proteins, it makes drugs. All complicated molecules nature is making. Just photochemistry, nothing else. There is no advanced laboratory. There is no vacuum system. There is no drastic reagents. There is no projects. But nature is doing wonderful. So, what I advise you is